Let's get started. It's my pleasure to introduce Raghuveer Garani, who has been on the faculty since 2024. Raghuveer works on astrophysics, astroparticle physics at the intersection of astrophysics, cosmology, and high energy. He obtained his BTech in chemical engineering from NIT Karnataka and his MSc and PhD from Bonn in 2017. Where he worked on dark matter phenomenology, n-body simulations, and supersymmetry. He went on to do postdoc at University Libre de Bruxelles and the INFN in Florence. His current research interests include gravitational particle production in the early universe and astrophysical tests of dark matter with neutron stars. With these, I welcome you to give the
Thank you for the introduction. I'm glad to be speaking here in this colloquium. I thought it was always reserved for invited speakers, not in-house speakers, but glad to know it has changed. So I'll be talking about how to make black holes from asymmetric dark matter. Essentially, this ties up three different topics. There is some overlap, but could be tangential. First of all, there is dark matter. I'm going to introduce to you what is the problem of dark matter. And then I'm going to tell you how black holes are typically formed through astrophysical processes. Basically, that is the Chandrasekhar limit, and how if you satisfy the Chandrasekhar criteria or exceed it, in principle, there's a gravitational instability and you collapse to a black hole. And then I'm going to describe a new way where you can, so the Chandrasekhar limit is a very strong parametric form. I'll tell you what it means. How to go about it by exploiting some phenomenological observations about number of space-time dimensions with you. Okay, so I'll go one by one and introduce these topics and then tie them up together into one story. So there is observational evidence for dark matter at various scales. Well, at the parsec scale, we do not have an observational evidence yet, but at kiloparsec scale, megaparsec scale, and gigaparsec scale, there are strong observational evidences for dark matter. So as there is matter in the name, it clearly tells you that it is something slow-moving, probably non-relativistic. And all of this is deduced from observing the two-point correlation function of the anisotropies of the CMB sky. And what you see here is that the first peak tells you how flat the universe is. So basically, this is about half a degree. And the difference between the second and third peak tells you the energy density in dark matter. And all these acoustic peaks comes from oscillations of the baryon photon plasma in a gravitational potential. So from the CMB, what we know is that we don't get a value for the mass of dark matter, just know that it interacts gravitationally and it is slow moving, that is non-relativistic. So at the level of galaxy clusters, we deduce the evidence, well, we deduce the existence of non-luminous matter. Basically, through gravitational lensing, you observe gravitational, all these nice arcs, which you often see in many of these pictures, which I don't show here, but essentially the observer is here, the source is distorted in a very peculiar manner as it traverses through a dark lens, or a lens which contains matter with zero electric charge. Okay. And further,
how do you distinguish between matter and dark matter?
It's luminous and non-luminous. I mean, dark means non-luminous. A more particle physics explanation is charge is extremely small or zero. Okay, down to galaxy level. So galaxies are roughly about kiloparsec scale. So, well, Milky Way is a bigger galaxy, but nevertheless. So typically we observe something called rotation curves, which is you look at the galaxy in the sky and you see stars going around it. And using Newtonian mechanics, you know that the velocity of the stars is proportional to the mass enclosed. And that's how you that's how you measure these dots. And then you deduce the evidence for dark matter because you see the luminous objects, you count them, and you see that you need to add an invisible component to be in agreement with the observation you see. So all these three evidences, all these three observations point to the fact that there is something non-luminous, slow-moving today. So at the solar system scale, it's interesting, that's what we are testing now with direct detection experiments, for example, or indirect detection and or collider probes of dark matter. And this is yet to be seen how this pans out. Here you're really testing particle properties. So overall conclusion from cosmological or the scale of variety of scale of observation is that roughly 25% of the energy density is in the form of non-luminous matter, non-relativistic non-luminous matter. So often we go to PDG to look at particle properties, and if you open PDG, we do not find this entry. Everything, we don't know its spin, mass, lifetime, decay modes. We don't know any of these things. But what we do know is we know that there is no electric charge. In fact, experimentally, you can have something called millicharge, which is not milli, which is something like 10 to the minus 18 units of electric charge is still experimentally allowed. It has no color charge. And again, because we see all these galactic structures, these have to be non-relativistic at the time of formation of first structures. And of course, it has to have a lifetime longer than the age of the universe. So put together, this forms a, well, this is a contemporary problem in particle physics and cosmology. And the main game here is to figure out what this particle is, or is it a particle? Is it a composite object like a primordial black hole? And how do you produce them in the universe, and in what novel ways you can test their properties, either in the lab or using astrophysical systems.
Why is it larger than the lifetime of the universe?
Because we see these gravitational structures today, right? Milky Way is embedded in a halo. If they were decaying, they would decay to something visible, neutrinos, photons, whatever, and we can measure them. And we can place a limit, and we see that that limit is much, much larger than the age of the universe.
That doesn't rule out things like WIMPs and so on.
No, of course not. WIMPs have a Z2 symmetry. Here, if I violate that Z2 symmetry, something can decay. So all of this is consistent with WIMPs, in fact. So weakly interacting, meaning almost very little electric charge, and non-relativistic, massive particle. So it is consistent with that paradigm. But as I'll show you, the problem of dark matter is not WIMPs or anything, is that there are too many of these things. So we don't know. So for every mass scale you choose, there is a prediction, theoretical prediction. As I said, all observational evidence point to the fact that there is some energy density in non-luminous component. That doesn't fix the mass scale. So for every mass scale you choose, theorists are very creative. You come up with all sort of scenario. And WIMP, you see, is a small blob here, which is roughly about, this is in electron volts. This is about GeV to TeV or 10 TeV, 100 TeV. Factor few there, doesn't matter. But you see there's a big landscape all the way from wave-like particles, like QCD axion is an excellent candidate for dark matter, and all the way to something called WIMPzillas, or even composite macroscopic dark matter, which is primordial black holes. And again, these are all theoretical predictions, and to test each of these scenarios, you really need different experimental approaches at different scales. Well, WIMP had historically been most sought after candidate, but given the current experimental limits and the status, people have been exploring other ideas as well.
Sorry, if you solve the dark matter problem, do you solve the dark energy problem also? That's independent.
They are independent, because dark matter just means its slow moving equation of state is P equal to rho v square. Dark energy has equation of state parameter -1. Yes. So these are different problems. Dark energy is a far more difficult problem than dark matter, because at least with dark matter you can use intuition from particle physics. Dark energy is really, we don't know yet what we have to do.
But dark matter will pass right through normal matter.
That depends on the cross section. So I'll come to that. So the current, so for WIMP, for example, the current experimental limits for around, the best experimental limit comes for masses around 30 to 50 GeV, and the cross section has to be smaller than 10 to the minus 47 centimeter square. So that is 10 to the minus 11 picobarns. That's the experimental limit.
So these WIMPs are something like neutrinos, or what? No, they are not.
No, they are massive particles.
They are massive particles, but weakly interacting.
Yeah, they are part of the, they can be part of the electroweak multiplet, but chargeless. They're the neutral component of the electroweak multiplet. And well, you can have a sterile neutrino, which is a pure singlet.
Yes.
That's different. And again, gravitino is a spin 3.5 particle. You can introduce it, you can play around with it. So theoretically, it's a complete playground, but the problem is not theoretical. The problem right now is coming up with interesting ways to figure out what we can do best, either in producing them in a novel way or in detecting or proposing tests to detect these things in an interesting way. Okay, so this is one part of it, dark matter. The second part, meaning I want to talk about Chandrasekhar limit. This is the basic story of how to go around the parametric formula of the Chandrasekhar limit. You would have heard of this, of course. Chandrasekhar studied here, well, not in IIT Madras, but in Presidency College. The story goes that he had this idea of Fermi degeneracy blocking gravitational collapse while on a steamer boat to England. Good for him. But the point is, you have gravity is attractive, so attractive forces pull you to the center, and when particles become degenerate, there's a Fermi pressure, and Fermi pressure balances gravity. So if you add more particles on top of this number, so let's say you need n number of particles of this sort to balance these things. If you exceed this number, there's a runaway solution, in the sense gravity wins over the Fermi pressure, and it'll all go to the center and form a black hole. That's roughly in words how it works. But we can do a little better than that. We can do a very pedestrian calculation to see how this works. You can understand all of this just by looking at total energy per particle. I'm writing kinetic energy, p square over 2m, non-relativistic here, and the gravitational potential. So this is a sphere of radius r with n particles. Okay. So when they become degenerate, while non-relativistic, p will go as n to the 1/3 over r, because interparticle spacing is whatever that is, and you get this formula. So if I minimize this, if I take dE over dr, I get a solution for r. So that r is this. So what this means is that for a given mass m, I can find, for a given mass m and number of particles n, I'll have a radius, a stable solution with this radius, which is parametrically proportional to m Planck square. Now if I start adding more and more particles, what happens is that r starts shrinking, and at some point the Fermi momentum becomes much larger than the mass, so it becomes relativistic. So when that becomes relativistic, total energy per particle, it will go as p instead of p square over 2m, and then it's simply n to the 1/3 over r. And here you see, when you minimize the total energies, the minimization condition gives you something independent of r, signaling a gravitational instability. And this number you get, n, m Planck cube over m cube, this is what is known as the Chandrasekhar limit. Again, this is for self-gravitating particles, meaning all these particles are gravitationally bound by themselves. So this is the so-called Chandrasekhar limit. As you see, this is m Planck cube over m cube. If I put m equal to 1 GeV, like neutrons in a neutron star, you will roughly get this to be m Planck is 10 to the 19 cube, 10 to the 57-ish. So you roughly get about half a solar mass, which is right in the ballpark of a neutron star. Of course, a neutron star, the actual mass is about 1.5 solar mass. That comes from additional short-range interactions that is not included in this calculation. So once you include that, you will get that. So the main point is that it's not an equality. This is similar to, the deepest insight is that it goes as m Planck cube over m cube. So for neutrons, we know this is how it works. But as I was saying, for dark matter, we do not know the mass scale. So we have a degree of freedom here with m. We can play around with this parameter. So I want to get around this parametric form, m Planck cube over m cube, because I have to add solar mass number of particles inside something to make it unstable. But can I do it with less than a fewer number of particles? So one obvious way is, what if I add an attractive Yukawa interaction that provides additional attraction, so to speak, on top of gravity? So you can ask, does the expression for Chandrasekhar limit change? Naively, you would guess yes, because more attraction would lead to more collapse or acceleration towards the center. But it turns out technically no, because there are interesting quantum field theory effects. Basically, the psi bar psi, or the scalar number operator, gets a vacuum expectation value at finite density. In vacuum, this bubble is 0, but in a medium, this is non-zero. This, in fact, happens also for neutrons in neutron star, where it gets an in-medium mass correction. And the bubble here tells you, because it's a fermionic bubble, you get a minus sign, and the mass inside the medium is smaller than the bare mass, depending. It's a self-consistent gap equation for the scalar condensate. So of course, this was figured out by Waleka in 74. It's an old story in the context of nuclear matter at high density, but it works the same way here. I'm just introducing a Yukawa force, and that's about it. So if I put all this together, I see that adding attractive interactions does not help. I get back because particles become relativistic nevertheless inside the medium. You need to have Chandrasekhar limit number of particles to actually cause some gravitational instability. So attractive interaction doesn't work, but so is there another way to do this? In fact, there is. Interestingly, well, Newton already knew it, that if I have a potential that goes as 1 over r square instead of 1 over r, in fact, you have a unstable configuration, while non-relativistic already. But how do we get this 1 over r square? I mean, it's difficult to get 1 over r square because we know gravity is 1 over r. So the point is, what if I modify gravity at short distances? Okay, that means modify gravity at short distances, meaning there could be extra dimensions at small distances that can give you 1 over r square behavior. So then I've introduced something new, extra dimensions. So what is this extra dimension? These are spatial dimensions. And how does this come about? So that's the third topic that I'm stitching together. So this is a picture of a torsion balance experiment. So there's a tungsten thread over here. And how this works is that you rotate the lower chunk, and the upper chunk oscillates it's a pendulum, it oscillates in a particular way. And you read off the torsion by shooting lasers against it. And looking at how the tungsten rod is bending, you can test gravitational inverse square force laws, meaning by changing this distance here. Okay. So what do we know experimentally or phenomenologically about extra dimensions? Before I get there, I want to make a comment that G Newton, although is one of the oldest constants we know, is also one of the poorly measured constants we know. Okay, so for example, of course, poor with respect to what you can ask, because I'm with respect to particle physics standards, which is at least fine structure constant. Okay, so G Newton is measured up to 10 to the 4 parts per billion uncertainty. Alpha electromagnetic, on the other hand, is really at 0.1 parts per billion uncertainty. So in that regard, it's a poorly measured constant, although it was figured out long ago. Okay, and then this is one comment. The other point is that there are many experiments, but the most famous one is something called the Eötvös-Washington torsion balance experiment. Eötvös stands for Eötvös, one of these Hungarian guys from long ago who pioneered this tungsten torsion thing. And there's a group by Adelberger company and gang basically in Washington who have the monopoly over inverse square law tests of gravity, and they place some interesting constraints on it. So the current test is basically they test potentials of this sort. Vn is the usual Newtonian gravity, which goes as 1 over r, and then they add an additional Yukawa-like force and place constraint on lambda and alpha. So as long as the minimum separation between two of those torsion balance things I showed you, the pendulum and the driving mass or whatever it's called, is larger than the size of extra dimension, this is a good approximation, and you can really fit this and find out what is the limit on alpha and lambda. This is what we get. Well, this is what they get. What one should...
So Vn is a standard 1 over r potential.
Vn is 1 over r.
And so then why not you expand the standard power law fashion like r cube, 1 over r cube, 1 over r cube? Why there is exponential?
I mean, they're explicitly adding a Yukawa-like force.
Okay, so this is their choice.
This is their choice. But when lambda is larger than r, you do the same expansion. Yeah. You get the same things. Okay. What we learn from here is that when alpha equal to 1, lambda or the range of interaction should be smaller than few hundred micrometers. So that is roughly here. So all of this in shaded region, they're all excluded. So this basically tells you that gravity is only tested up till few hundred micron level. Below that, inverse square law is not tested at all. Okay.
I thought it's a manageable distance.
No, what is, I mean, of course you can say I have a microscope, so what? But that's not the distance I'm talking. The distance we are talking about is the interparticle distance. You need to have a finite density setup where interparticle distance can be tested, where you have freedom over the interparticle distance. Okay. So, for example, I'll come to astrophysical test where that becomes.
Somewhere in the nanoscale, nanometer scale.
This is micrometer. The limit is at the level of micrometer.
Yeah, now is micrometer. So you want to properly test the distribution somewhere around nanometer scale.
Yeah, but it's a very difficult experiment.
Of course,
Yeah, people are trying. That's what they're doing. You see, they're slowly.
What was the limit Cavendish and people like that? What was the distance over?
I mean, Cavendish experiments, they're somewhere here to the right. And slowly you see 2004, 2007, 2020, they're like slowly moving to the left. It's very difficult experiment because you are very sensitive to
What is the limiting factor? Or maybe
noise. It's very difficult to maintain interparticle separation of your desired amount to get the limit. So when you go to the frequency space, you see a lot of oscillation and it's difficult. That's what I gather.
So can I just ask when you say that the universal extra dimension exclude up to a few hundred microns, it means that the dimensionality of the compactified object should be less than a few hundred microns?
Yes.
That's what it means.
That's what it means. So this is one of the tests of inverse square law, but there are more interesting tests possible, especially at colliders. So this was very fashionable or very popular in the 90s when a bunch of people came up with having extra dimensions like Arkani Ahmad, Dimopoulos, Dwali, and Randall Sundaram. There's a whole gang. So here the idea is that you simply collide quarks, antiquarks, whatever. This is for the tevatron, but it doesn't matter. Particle, antiparticles collision. You can look at Drellian-like process or whatever. And then what you look for is missing energy. And if there are extra particles, you'll see a difference in particle distribution in your differential cross-section, what you're measuring. So from that, people have derived limits. For example, Atlas a few years ago put out this limit as a function of number of extra dimensions and the scale of extra dimension. So MD inverse will give you the distance. So MEV is like 200 MeV is like a femtometer. So TV is smaller than that. Okay. So generally, as you increase dimensionality, limits become poorer and poorer. Well, this is the 8 TV one. This is the 13 TV one. Probably there's a newer version which I'm not aware of, but roughly the limits go like this.
These are extra dimensions assumed like the Euclidean dimensions.
These are universal extra dimensions. They are not compactified yet. So limits on universal or large extra dimensions are extremely strong. Okay, so but we're going to exploit this fact that if you compactify it, you can get around this. Okay. So the strongest bound, in fact, comes from stars or supernovae, because they're in fact interparticle spacing, because they're at large densities, are of the order micrometers or smaller. Especially from supernova, you see that if there are if gravity propagates in extra dimensions, there'll be a loss of flux and the rate of cooling will change, and looking at the observation, you can draw constraints. So from stellar cooling bounds, you see that the scale of compactified extra dimension can be smaller than half few millimeters. This is similar to what we had before. Yeah.
Just a basic question. So, is there an intuitive way to think about what it means to talk about the size of extra dimension?
I'll come to it in the next slide. Okay. Anyway, here I wanted to indicate that roughly this is the size. I'll come to that. Maybe I can jump to it right away. So this is what I mean. So I have time, space. This is a universal extra dimension.
So I just had a question on the previous slide. So does this drop off essentially as an order of magnitude per extra dimension?
So you can do this calculation on dimensional grounds just because phase space increases. When you do the phase space integrals for the cooling rate, you get an extra factors over there. So 1 over r's, it's easy to get 1 over r's from that. So just if you do dimensional analysis, you'll roughly get these numbers. So it's a straightforward calculation.
So in the previous slide where you showed the experiment of quarks and antiquarks. So what are we concluding here? And from the graph, what are we seeing?
So here, quark and antiquark annihilate, a gluon is produced. Typically, the possible final states are either bunch of quarks and antiquarks or bunch of gluon jets. But you can have, if you open up the possibility of extra dimension, you can have a gluon and a Kaluza-Klein particle coming out, Kaluza-Klein mode coming out. So that's an excitation, and that is not detected. So this goes under missing energy searches. You roughly know the initial energy. You know a jet is coming out. So you put a cut on the final energy of the undetected particle and try to estimate within error bars whether you can exclude something. Okay, before I move on to the next one, just a final small comment that in fact gravitational waves can also put limits on extra dimensions, but current LIGO limits are quite poor. It is projected that something like LISA or Big Bang Observer can put stronger limits of the order micrometre for n greater than or equal to 2. Okay. And again, this has to do with the same thing. Phase space increases with extra dimensions, so there will be a leakage of flux. By comparing your waveforms or whatever spectrum, you can get a limit on these quantities.
Sorry, what is n here?
Number of extra dimensions. So if 3 plus 1 plus n.
Projection is through squeezed light.
Squeezed light. Energy is too small. I mean, maybe you can devise something. I'm not aware. So how to imagine it? So normally you put all the known 3 space on one line, and universal extra dimension means there's an extra 5th dimension like that. Compactification means you bring it down on a circle. So this is now a 3 space. So every point in a 3-dimensional space, there's an orthogonal circle on it. Okay. So this is for one extra dimension, one compactified extra dimension. In fact, typically what people do is they do toroidal compactification. So you'll have toroids at each point in x, 3x. Okay. And that's how you can roughly try to imagine. So then given all these phenomenological inputs and problem of dark matter, Chandrasekhar limit, and limits on extra dimensions, I put it together. I use that to set up the scenario or the assumptions for what I want to say. That is how to change the parametric form of the Chandrasekhar limit. So this is the setup. The setup is I assume there are d compact extra dimensions, toroidally compactified, and they all have the same size, some whatever r star rd over 2 pi. At low densities, so because we are in an effectively 3-dimensional world, I'm looking at a system where I have a gravitational potential and I'm adding fermions in it. And at low densities, fermion populate only the zero modes, that is effectively the 3D. At high densities, as the momenta increases, there's a perpendicular component that goes like that, which is again in the non-relativistic limit. This is p square over 2m, but because it is compactified, p has periodicity n 2 pi over r, and that's this factor here. And you sum over number of modes and number of dimensions. So this will be your dispersion relation. This will be your dispersion relation in the non-relativistic.
So number of modes should.
Sorry?
Is the time also orthogonal to the extra dimensions?
Yeah. The time is orthogonal to everything. Well, we are in Minkowski. Well, that part is in Minkowski, so they're always orthogonal. Then there's only one time.
Is it given in relativistic?
Yeah. I mean, this is my geometry of the problem.
So the number of modes available would be proportional to r, right?
Well, as this, yeah. 1 over r square.
So allowed interparticle distance.
So if you increase density, you'll start discretely filling up more and more ends. That's the idea.
So you're just going to repeat Chandrasekhar with this sort of. So
Yes, I'm gonna do the. I'm gonna construct the equation of state for this, and then put it in hydrostatic equations and see what happens. Okay. So the minimum excitation energy has to do with what you said, happens for n equal to 1. I'll call it E star, which is n equal to 1, goes as 1 over 2m r star square. That is E star. For a three-dimensional non-relativistic Fermi gas, it's well known Fermi energy goes as number density to the 2/3, and higher energy levels will be occupied when Fermi energy exceeds this E star. This is the minimum energy you need to start occupying extra dimensions. So from here, you can construct a critical density in the non-relativistic limit, which is simply mass times n star. So n over v is the small n, and I'll call it star because I'm comparing, I'll set this to be an equality. And we say that, so in a given volume, if the energy density increases this quantity, m over 3 pi square r star cube, which is just inverting all of this and equating them, we'll claim that extra dimensional phase space will start to be occupied. Okay. When you put in the numbers, you see that for a TeV scale particle, you can, and if the size of extra dimension is like 1000 Fermis, you need about 10 to the 8 gram per centimeter for this to work, centimeter cube, for at least the first excitation energy to be filled in extra dimensions. Okay, is it clear? Okay, so few comments. First thing, so that what I said there was effectively 3D, and I'm equating things 3D, but then there is gravity, which we allow them to propagate in extra dimension. So in this scenario, we have dark matter, which is for all purposes here is just another dark fermion, propagates on the brane and the bulk, and gravity as well propagates everywhere. So if you apply Gauss's law, you will quickly get how the Newton constant in 3+1 dimension is related to Newton constants of higher dimensions, or M Planck of higher dimensions. And again, this simply has to do with the area integral here, and it's straightforward to see how you can get a potential of 1 over r square just by doing Gauss's law. Of course, this only is true if you are completely inside the extra dimension, if all the modes are inside extra dimension. If they are not, this is not always followed.
So this I don't understand, because so the number of allowed states in the extra dimension are discrete, right?
Yes.
So how do you just simply extrapolate the Gauss law to this?
No. By doing this, these are two cases. In one case, I say it's a 4-dimensional volume. In the other case, it's a 4 plus d-dimensional volume. I'm not interpolating between them yet.
Yeah, but in the d-dimension, number of allowed states are discrete.
Yeah, no. Here I'm assuming continuum. I want to get the scaling.
This is for non-compact.
This is for non-compact. Yeah. This is just to get the scaling of how the potential will look once you're inside. Okay. Just a comment. And from here, we'll go on to the actual summary of the scenario, which is basically I'll collect some particles in a gravitational potential, let it thermalize and become self-gravitating. In the usual scenario, you put Chandrasekhar number of red particles, it'll collapse to a black hole. In this scenario, if you exploit the fact that there are phenomenological possibilities for extra dimension, you see that phase space begins to be occupied beyond some critical density, which is rho star. And then this will induce unstable orbits. That is, you become hydrostatically out of equilibrium, and this leads to collapse of black holes with fewer number of particles. So graphically, this is the whole story. And I motivated how we can do this. Now I'm going to tell you, I'm going to construct the equation of state for these fermions to show you how the equation of state softens because of extra dimensions by discretely filling it.
So if they don't interact with each other, how do they thermalize?
They thermalize with the background object. So there I'm assuming there is a very small interaction with, say, background neutrons or protons or whatever there is. Okay, so now the goal is to construct the equation of state, which is pretty much standard calculation. The only added thing here is that I'm discretely summing over the perpendicular momenta. And the perpendicular momenta, again, I rewrite the dispersion relation. This is a fermion at finite density. Again, this is the 3-dimensional pressure and energy density. So they still have units of energy to the 4. Okay. And this is what we are interested in because we want to see the 3-dimensional stability. And then you go through this calculation. Of course, in the 0 temperature limit, you get these theta functions and it becomes easier. At finite temperature, you can keep the temperature dependence and work through all of the algebra and integration.
Is
there some assumption that normal matter cannot get into those extra dimensions?
So normal matter is stuck on the brain. That's the construction.
And you assume things like spin statistics and so on, even for the dark matter.
Sorry?
You assume spin statistics connection, for instance, you said fermions.
Yeah, we assume, yeah. So, sorry?
What is the brain you're talking about?
No, this is the 3+1 dimensional sheet here.
Yeah.
And then for all standard model fermions are stuck over there.
No, but I thought your extra dimensions were there everywhere.
They're there everywhere, but by construction, standard model fields for now is not a function of.
Some random Sundaram type of.
Yeah, okay. I can speak in that language, but
Okay.
it's warp space dimensions, but I'm not talking about warping yet.
So normal matter hasn't noticed the extra dimension there.
Well, there are stronger limits. Well, there are limits, but it doesn't notice it by construction. It is localized only on the 3+1 dimension.
So here we are summing over the extra dimensions, and P perpendicular is the momentum in extra dimensions.
Yes, so when you write the energy, this p square over 2m is the three-dimensional one, and then p perpendicular over 2m, and this we sum discretely because p perpendicular goes as n over r.
Okay, so in the energy density equation where we are doing d3p,
Yeah.
why are we not doing 3 plus p like the extra dimension?
So because I'm by definition I'm constructing the three-dimensional energy density, not d-dimensional energy density.
But sir, we are summing over the extra dimensions momentum. So how like this is how like we are defining here?
Because we are not yet gone to the continuum. There are very few, you're slowly building it up.
Maybe you should tell us the sum is over those quantum numbers n1.
Yeah, this is sum over n. Maybe I mentioned that.
One more.
Yeah. So you see this p perpendicular is this, n equal to 1, 2, 3. So because you are slowly increasing density, first the lowest modes will be occupied first.
So, for example, solid state, you can say quantum well.
It's exactly that, different words, but same thing. Yeah.
Is there bound to the number of accessible extra dimensions, like the D itself?
So there is a, as I said, for 2 extra dimensions, you should be smaller than micrometre. There can be many. String theory can allow for 10, 11, it depends. 6 compactified.
Because 4 are there.
Okay, 6 compactified, yeah. So, huh? 10. I mean, Suresh is there, he's going to explain it to you. Why 10, how Veneziano amplitude from 26 reduces to 10, he's going to explain that, but maybe in a different colloquium. Okay. So this is the equation of state. So I run through the whole thing for different dimensionalities. 0 is the normal 3+1 dimension. Of course, it's all normalized to, energy density is normalized to mass, so this is dimensionless. And what I'm plotting on the y-axis is the polytropic index, which is d log p over d log rho. And at low densities, ideal gas, p equal to rho t. As I increase my density, you get Fermi gas, non-relativistic Fermi gas, which has an exponent rho to the 5/3. And then as you continue increasing your energy density, at some point particles become relativistic and p will go to rho over 3.
So these are dark fermions.
The statement I'm making is very general. Okay, I'm not yet, because I've normalized all of these things to, it's all dimensionless now. So now I open up one extra dimension. So at low densities, the behavior is the same. It becomes a non-degenerate Fermi gas. But beyond some critical density, I start filling up these extra dimensional states. And then you see these oscillations. So you discretely start filling it up. As the density becomes more and more, you go to the continuum limit and you become smoother. And as you increase more density furthermore, you become relativistic, but at a later time, compared to the d equal to 0 case. So again, you go back to p equal to rho by 3. And if I move to higher number of extra dimensions, 2, 3, 4, it's similar behavior. Just because there is multiplicity in number of directions you can fill, because there is n1i, n2i, n3i, and so on, number of oscillations, there's There are minute oscillation on top of each of them, which you don't see very clearly here, but the overall trend remains the same, that there is some wild oscillation and then it asymptotes to p equal to rho over 3. But in a particular regime, you see that the polytropic index decreases from 5/3 to all the way to 9/7 as we go from 0 dimension to 4 extra dimension. So this is the softening of the equation of state. So from here you can already guess, because the equation of state has softened, if I put this in hydrostatic equations, there will be an instability sooner. That's what I will do next. So hydrostatic equation, okay, these are the standard part. Kinetic energy is in the pressure part, and the potential energy is in rho and phi, and you have the Poisson equation. You have to solve the Poisson equation along with this together, and you will get something called the Lane-Emden or Chandrasekhar-Emden equations in the non-relativistic limit. If you do the relativistic generalization, you will get the Tolman, Oppenheimer, Volkoff equations. So what I'm going to do is I'm going to solve these equations by using the equation of state I showed you before. That's it. But you have to be a little careful here, because I'm solving it from an effective 3-dimensional perspective. As long as I am at distances larger than extra dimension, the gravitational potential simply gets some correction of this sort, because the Green's function changes. But for particle separation much smaller than the size of extra dimension, the gravitational potential is different, 1 plus.
Not r squared.
So there's a 1 over r outside.
Yeah, so it becomes r cubed.
Yeah, there's r star square over
I
there.
understand that.
Yeah, exactly.
Little r.
Yeah.
There's no 1 by r term.
No 1 by r square term.
Yeah.
Yeah. Function. There is this paper by Garriga and Tanaka from 99. Anyway, for particle separations much smaller than the extra dimensions, you will see that the potential will go as 1 plus d. Then you'll have to redo the whole calculation through the Green's function, and it's complicated. So I will not do the second part. For good reasons, I will show you why. The reason being, for some dimensionality, already you see instability when you're non-relativistic and in this regime. So once the instability sets in, this is not going to save you. So that's my argument, but we are working on how to figure that out. Okay, so hydrostatic equations. So plug those things together, and I'm writing in something called Landau units. Everything is dimensionless, so you solve it once and change variables to get your solutions. There are two possibilities. One of them is self-gravitating configurations. That means particles, they're sourced by their own potential and they're evolving by themselves. The other one is that there's a background potential and particles are evolving in the background potential. Okay, these are two possible configurations you can have. So I'm running out of time, so let me come to the solution. So the mass radius relation is shown here. R bar is the dimensionless mass, the dimensionless radius, and m bar is normalized to the Chandrasekhar limit, and r bar to the Chandrasekhar radius corresponding to Chandrasekhar limit. So when d equal to 0, when you're non-relativistic, it's simply this black line over there for self-gravitating configurations. For non-self-gravitating configurations, meaning initially you're dominated by background objects, background energy density, you start here. As the density increases, eventually you become self-gravitating and join that line, which is logically acceptable. So what happens when I open up extra dimensions? So this star corresponds to central density equal to this rho star, where the first mode is occupied. And this also corresponds to a specific mass, which is the Chandrasekhar mass here, times a factor, which goes as rho star square root divided by m square. This is the parametric change in the formula, and this we can extract it analytically by solving these equations in certain limits. So for one extra dimension, we see that there is some bending and it goes away. So basically configuration becomes compact, but d equal to 1 and 2 are not conclusive in the sense we need to do more work to make a robust statement because of this problem which I mentioned, because this part is not clear, because what that shows, that does not show instability. It just shows that there is a solution, but to figure out whether there is an instability, we have to do this part. But for d equal to 3 and 4, they are unstable because clearly you see there's a maximum mass. So if you go beyond this maximum mass, everything falls. So this is like critical, and for dimensions larger than 3 and 4, these configurations are indeed unstable. There's another way to see this. The other way to see this is to perform a linear stability analysis on the hydrostatic equations. So basically you introduce a time-dependent perturbation and see what is the eigenvalue. The problem reduces to the Sturm-Liouville eigenvalue problem. If the lowest eigenvalue becomes complex, it shows that there is a growing unstable mode. And that happens, there's a well-known result, and you can find it in Shapiro and Tucholsky. It's the same Tucholsky who wrote numerical recipes. So he has done many things. And the main result is that if you do a pressure average polytropic index, if that falls below 4/3, all those configurations are unstable and nothing can save you. It'll all go through a singularity, it'll probably collapse to a black hole. So this happens while it's non-relativistic, and I don't have to worry about these short distance corrections at the moment. However, for d equal to 1 and 2, although equation of state softens, it doesn't become critical or unstable due to perturbations. So 1 and 2, I'm not sure, but extra dimensions compactified with dimensionality larger than 3 seems to indicate that things are unstable. Okay.
Don't look at that.
Okay.
519.
519. Okay, I think I can make it. So now I'm gonna. Yeah.
I'm a little lost, but let me try with this. You choose this 10 to the 4 for the dimensions times the mass of whatever this
Yeah.
is. How does all this vary if you can change that, right? That's a choice.
You can change that. Parametrically, these oscillations slightly move a bit, but for d equal to 3 and 4, the main thing is that the shape might change, but they fall below 4/3 for d equal to 3 and 4 for a various range of phenomenologically allowed values of R star.
That was my question.
Yeah, that we have checked, and that's what we show here. Okay, so now all of this, for all of that purpose, we were independent of dark matter or not. It was simply a fermion. Now I'm going to assume that, okay, that fermion is dark matter. So the current idea we have about dark matter is that we are in a thin disk. Baryons form a disk because you can lose angular momentum by emitting photons, so you can collapse. But dark matter does not lose angular momentum. There is no light mediator over there, so it forms halos, virial spherical halos. And there's some stars inside these things.
Spherical or ellipsoid?
Ellipsoid is more general solution. Spherical is the easy way out. Triaxial, to be precise. Triaxial. But okay. The point is, now if you have these dark matter, there are also stars around. So once in a while, all these dark matter particles pass through the stars. They interact with objects in the star, lose kinetic energy, and get captured inside the stars. All of this is like old story, and dynamics is really covered by a very simple Boltzmann equation of this sort, where C is the accretion rate, annihilation rate, and E is the evaporation rate. Of course, I'm talking about something called asymmetric dark matter, meaning just like there is more protons than antiprotons, I'm assuming there's dark matter of one type and there is no anti-dark matter. So I'm forbidding annihilations so that I can get maximum number of particles accumulated inside the sun. Okay.
So you've decided that this stuff is completely, there's a huge CP asymmetry.
So I have assumed that there is some mechanism that has set in an asymmetry, just like in the standard model sector. A generalized version of a mechanism that set asymmetry in the standard model sector. Okay, there I can make more comments. If I turn on this annihilation, what happens is degeneracy factor decreases. Instead of a Fermi-Dirac distribution, I'll have a Boltzmann distribution, and you can redo the whole calculation, and you get a similar equation of state. So once this happens, there are a few possibilities. Like if you allow for annihilation, you can get neutrinos. Well, you annihilate to everything, but neutrinos escape because neutrinos of low energy escape. High energies are stopped. you can form black holes, which is what I'm after. And then you can also heat up cold objects like cold neutron stars or whatever. So let me come to the black hole story. So before that, I want to give you a very pedestrian perspective of how this capture works. In the end, everything, as in particle physics, everything depends on the cross-section. Here, this is the rate of particles that accumulate inside is just proportional to the flux. And this is nothing but the maximum impact parameter. This is the number density, and this is the velocity. That's it. So this is sigma, n, and v. So you get units of per second. This is the rate at which particles are hitting this object of radius. Here, it's the sun, doesn't matter. What I'm assuming further here is that the cross-section is large enough such that it gets stuck after one collision, which is good enough for what I want to describe. So you can define something called a geometric cross-section, for which mean free path combination of this is order 1, meaning it'll interact very rarely. If you're above this number, you interact more often. Okay. So when you put in all these numbers, you see that a typical geometric cross-section for the sun is like a pico-1, white dwarf is like 10 to the minus 39, and neutron star is 10 to the minus 45 centimeters square. And maximum amount of debris or dark matter stuff it can accumulate is of the order of 10 to the minus 10 solar masses, very small number. But what happens is that all of them are accumulated in a small region, and a black hole can form there. That's the idea. Okay, so to check, to impose, to basically extract limits or try to get some parametric behavior of R star, mass, and cross-section, these are the 3 parameters in the game. I say that the maximum mass accumulated in a star is like mass times the rate times the time. Time here is like giga-years, 10 giga-years. That's the oldest neutron star we know. So you get 10 to the 9, large numbers, 10 to the 17 seconds, in fact. And if this number is larger than the critical mass in the extra-dimensional scenario, I claim that a black hole is formed. So for d equal to 3, the parameters are roughly of this sort. You can start forming black holes if dark matter is of the order TeV and radius is of the order hundreds of femtometers. The point is, so far is okay, but how do you put a limit on this? The limit is that you form a black hole, and black hole doesn't sit there. It does things, it eats things around it. So it accretes, it becomes fatter and fatter. Eventually, given enough time, it'll accrete the whole star. So if this is happening in a neutron star, what happens is that instead of seeing neutron stars in the sky, you will see solar mass black holes, which is hard to see. But the fact that we are seeing very old neutron stars of ages of order 10 giga-years tells you that this mechanism has not happened. That means I can place limits on combinations of these parameters. That's how you draw a limit in this case. Okay. So once I form a black hole, okay, these are formulas, but I'll not get into the formula, but you have to check for 2 things. So the black hole mass evolves. There's an accretion term and an evaporation term. Accretion term is, for all practical purposes, you can assume it to be Bondi type accretion, cross-section times number density times velocity as usual. And evaporation is Hawking evaporation. If you put these 2 things together, you can work out a time scale for which one or the other dominates. Okay. You do all these numbers, but let me come to the main result. So this was done in, this paper took a few years, 3-4 years to work out. There were a lot of very annoying things to figure out. So this is with my former employer, Michel Titgart, and other collaborators, Chris Couveris and Jerome Van de Castel. And these are the possible parametric regions you can test. So on the right-hand side, I'm fixing the cross-section to be a geometric cross-section for neutron stars, which is 10 to the minus 45 centimeters square. And here we see that there is a red region where, in fact, you collapse to a black hole and eat the whole neutron star, and you should not be seeing any neutron star in this region. So if mass is around TeV and about femtometer or below, neutron star should not exist. Neutron star of age 10 giga-years should not exist. But they do exist, so this whole region 1 is excluded. Region 3 is where the usual Chandrasekhar limit holds. Usual Chandrasekhar formula is recovered. So of course, when extra dimension becomes extremely small, it's as good as a usual 3-dimensional effective theory. So you recover that limit very nicely, continuously. So there are green regions where you form a black hole, but then it evaporates before consuming the star. So you cannot place a constraint. And then there is this other region where it is unstable but does not collapse. So there is a radial mixing of things going on, but it does not coherently collapse to the center because there is no energy evacuation mechanism. So, and of course the white regions are totally unconstrained. So in the standard scenario, typically you end up constraining only this part, which is 10 to the 9 GeV, 100 PeV or more. But if you allow for extra dimensions, you can somehow, it's a 3-parameter game, so there's always some region which you can test in some way, under some assumption.
It's for only one extra.
This is for d equal to 3. So d equal to 1 and 2, we are not confident in making a statement, but d equal to 3 and 4, yes, because of linear stability analysis. And then on the left-hand side, I'm fixing d equal to 3 and the size of extra dimension to be femtometer. And here you see that this region of cross-section in fact could be excluded, and this does much better than the current direct detection limits which you see in this yellow line. In fact, there is something called a neutrino floor, beyond which statistically it's very difficult to improve your statistics in a direct detection experiment, but astrophysical probes of this sort, while construction demands some thought, you can still probe such regions. So this was the basic. So we had to do all of that, exploit many things to finally come to something of this sort. So anyway, it's an exercise. We have to know where the buttons are to know what to push to go where. I mean, it's a theoretical thing. Okay, so this brings to my conclusion. Neutron stars provide an interesting playground to test all of these crazy ideas. So for d larger than equal to 3, in fact, the Chandrasekhar limit or the parametric formula or form of the Chandrasekhar limit can be modified in the right direction, in the sense that works to our advantage, meaning you can collapse with fewer number of particles. And one needs to work out long distance, short distance corrections to hydrostatic equations for d equal to 1 and 2, and that is something we are still doing. So with this, I would like to end, and thank you for listening.
Can I ask something probably very stupid? What's the typical size of these black holes?
RBH, the horizon size.
What's the typical size? I mean, how many?
It depends on dimensionality and the size of extra dimension. So d equals 3, well, you have to plug in the formula. You are asking me for a number?
I mean, scale.
Smaller than femtometer.
Smaller than 50.
Yeah. So these are all d-dimensional black holes. So it will be smaller than whatever y-axis I'm quoting. So if I'm here, the seed that has formed, it will be much smaller than this.
So this is very nice. So these black holes are some femtometer.
Yeah.
What possible way can I measure? I mean, it's a stupid question, but how do I?
You cannot measure that. It's happening inside a star in a very dense medium. But it accretes. That's the point. You have to wait for it to grow. So the thing is, it's smaller than the size of extra dimension, so it's an extra dimensional black hole.
Right.
And then accretion happens in that regime through Unruh accretion, in the sense it's not geometric. You have to sum over the partial waves. The cross section is different. So it's what's called the wave limit in optics. Once you do all of that, it will accrete matter around it, and eventually it will grow because mass is increasing. And at some point, it will become larger than the size of the extra dimension. At that point, it becomes effectively 3D. And then eventually it will start growing and consume the whole star.
It just happens somewhere. You have certain linears of the.
So the thing is, yeah, we have seen neutron stars of age 10 giga-years. So if such things have happened, that star should not exist, but it does exist. So that places some limits on these numbers. So it's not a detection, it's a constraint. That's the best you can do.
Just general question. Isn't dark matter supposed to be at the edges of galaxies?
It's supposed to be there everywhere, even here.
Everywhere between the Earth and the Sun.
Yeah. So the density of dark matter is at least 5 times that of standard matter, right? So we have plenty of standard matter here, but there is a limit at the level of, by measuring the vertical motions of star, you know the gravitational potential at the position of the sun, and this gives you a limit of about half GeV per centimeter cube for dark matter. I mean, you need that number to explain the vertical motions of star or vertical acceleration. So that is the energy density of dark matter in a circle of about 500 parsec around the sun.
So I thought Raghuveer's original observation was the edges of galaxies in the rotation curve.
Because
Yes.
you expected drop and it didn't happen.
Yeah.
That's all. So for that there is no, because in that region there is no visible matter.
Yeah, but now observations have improved precisely by looking at the AZ acceleration along the vertical direction perpendicular to the plane of the stars at the solar position. You get this number, that you need dark matter of density half a GeV per centimeter cube at the solar position.
Suppose I have a dark hole, dark matter black hole which is formed, which is big. What will be the nature of Hawking radiation? Will it be dark photons or photons?
It'll be everything. Hawking radiation doesn't discriminate. I mean, it'll be everything. It's proportional to temperature. If something is massive, if the temperature is above that mass, then it'll emit it. So in the end, it'll be radiation. Yeah.
Can we not do linear analysis for d equals to 1 and 2 and try to figure out the parametric form of the spatial limited the way you did for the others? D greater than equal to 3.
Yeah, no, we did that. So this is the result of the linear stability analysis for d equal to 1 and 2. The fraction here you see is still 3/2 and 7/5. But we can be sure that when the index falls below 4/3 or equal to 4/3, it is truly unstable and it will collapse. So here something is happening, but we don't understand what is exactly happening. It's becoming soft, probably it's not collapsing, but to really see that, I need to include short distance correction to the gravitational potential.
And why is it that not relevant for d greater than equal to, like what is it changing when we are going to higher?
So this is at this level. So G Newton, when distances are large, it will simply go as this. This is an order 1 correction. But you are integrating this as a function of radius, right? So you start with the central density and you move out. So at the very center, at very small separation, the gravitational potential is 1 plus d, not of this form. So then I have to change all of these equations. Again, these are all gradients for 3 dimensions. These are effectively 3-dimensional parameters. If I'm resolving the extra dimension, all of this has to be d-dimensional. And then you have to match it on the boundary and do it. But for d equal to 3 and 4, we already see that in this regime, it is unstable. And gravity is always attractive, and there are no finite density effects like the vacuum bubbles. For spin 2, that is 0. So it doesn't contribute to mass. So that's the reason. So for that, we need to do a lot more work to make a concrete statement for d equal to 1 and 2.
And if you look even larger d values?
For larger d values, the story holds. So d, 3, 4, 5, 6, all of them will fall. All of them, they're all unstable. Well, this matches with the intuition that there are no stable Keplerian orbits in higher dimensions.
Sir, where you showed the graph of the regions, where the different regions were there.
Yeah.
So, sir, here we are putting the limit on the dark matter size or something like that.
Here, in one case, I'm fixing the size of extra dimension. So it's a 3-parameter problem: mass, cross-section with neutrons, and the size of extra dimension. So I'm showing a 2D plot. So I'm fixing one in each of them, a different one. In one case, I'm fixing the size of extra dimension. In the other case, I'm fixing the cross-section.
Okay. So, sir, the unstable part, you said that in the unstable region, the black hole will be formed, will be unstable. So
No. We don't know black hole will be formed. It's just that the configuration is unstable. Configuration is unstable can mean that there is radial mixing. So there is convection. That's also a sign of instability. But for that, we need to do a lot more work to make a precise statement. But we know that it is unstable, but we are not sure that it collapses to a black hole.
And so the gray region there.
So in gray region, you are not degenerate. Density is too low to be degenerate.
Just one random question.
Yeah.
Is your assumption of fermionic degrees of freedom based on the prejudice that there's supersymmetry in that thing somewhere?
Yeah.
And dark matter is 14 nodes or 17 nodes or whatever.
Well, it's not based on that, but this also works for if something works for fermions, it will work for bosons. So there is no prejudice there, but it's
But
Pauli pressure. But the boson, you don't have Pauli pressure.
but for bosons you have self interactions that will act like a pressure. If you have a lambda phi 4, it will act like a pressure because particles are meeting each other and exchanging momenta, so that will act like pressure.
Lambda phi 4 in that many dimensions.
Well, lambda phi 4 in Lagrangian, I can define the measure to be in whatever dimension. So lambda phi 4 is still renormalizable in 3+1 dimension. I'm integrating over the extra dimensions because they're all compactive. Sorry?
If you repeat the analysis,
Yeah.
bosonic pressure,
Yeah.
the threshold D might change.
Yeah. Qualitative story will hold, but numbers and
You might find that D equals 1 is unstable enough.
I'm not so sure. I have to think about that.
You mentioned direct tests for dark matter at the solar system level at the start of the talk. What do those look like?
This solar system, in the lab you mean?
Yeah.
So there's something called direct detection experiments. These are super cool liquid xenon or some noble gas deep underground. They just wait for some exotic event, a particle to come in, deposit energy, and they can measure the recoil or measure the energy loss. And whether having observed it or not, you can detect them, constrain them, whatever. So that's why they're deep underground and they're shielded. Neutrinos have a very specific signature. WIMPs have a different one. Neutrinos undergo charge current interaction, but these are all only neutral current interactions, at least for the zero multiplet.
Why does that serve as a test for dark matter specifically?
Why does that serve?
Like as opposed to other particle collision tests?
No, but this is a particle collision test. You're testing cross section and mass.
Right. So how does this specifically give us a measure of dark matter?
Because you are using your knowledge, you're using what you know about standard model particles and you're shielding it in a particular way. So muons cannot reach them, neutrinos can reach them, of very low energy neutrinos. So all of these experiments have a threshold beyond which something can be tested. Some of this scenario can be tested, or dark matter hitting them can be tested. Below that threshold, there will be neutrino events, but above that threshold, you expect no neutrino events. Because as neutrino energy increases, the cross section increases, so they get stopped in the rock or wherever.
One more question. Based on the Fermi gas idea, you said a minimum density threshold beyond which the extra dimensions get populated.
Yeah.
So why does that happen only after a threshold? Why does that? I mean, the goal would be to minimize the overall energy of the.
No, it's nothing to do with minimizing energy. It's simply I have a dispersion relation. So this is the dispersion relation. And Fermi pressure, Fermi energy we know in 3D gas. And if this number exceeds E star, I'm simply saying that the wave packet will now extend also to extra dimensions. We'll have enough energy, their momenta will be enough to squeeze in the extra dimension. Otherwise, the wavelength will be large and extra dimension, you just go over it.
All right. So let's thank Raghuveer.
Thank you.
I request Chandrasekhar to give a memento to the speaker. Thanks.
Thank you very much. Thank you.